Eos Chasma spreads as a stripped basalt plain east of Valles Marineris. The ground looks scraped raw. Dunes and ripples sweep across eroded craters. Reddish-brown tones point to old basalt, worn down over immense time. Water likely played a major role in this erosion. One crater cuts deeper than the rest. Its walls expose sharp color contrasts. Bluish areas mark fresher, boulder-rich basalt below the surface. Lighter material near the base suggests a different composition. The crater floor matches the surrounding plain, filled by sediment carved elsewhere and delivered by wind. This landscape records repeated removal, transport, and exposure of Martian crust. A wide valley floor narrows into a layered system of channels. Smaller channels carve into the base of a much larger one. Flow once concentrated here. One branch pours directly into a crater, focusing movement into a closed basin. The other branch dissolves into a tangled network of minor channels. Energy drops. Direction shifts. This pattern shows that transport did not happen in one simple episode. Movement changed over time, splitting and weakening. The valley preserves a sequence of flow organization, revealing how fluids or debris adapted to subtle changes in slope and resistance across the surface. Steep slopes here remain active. Gullies slice cleanly into the terrain. Carbon dioxide ice freezes, then rapidly disappears. Defrosting triggers sudden motion. Material collapses and surges downslope. These gullies are not ancient scars. They are alive to seasonal change. Mass movements reshape the slopes repeatedly. Mars shows that cold-driven processes still move large volumes of material today. No rainfall is required. Phase change alone provides enough force to cut, transport, and rebuild surface features on a human timescale. The southern polar region quietly transforms through sublimation. Solid carbon dioxide turns directly into gas. No melting occurs. Ice vanishes from beneath the surface. Support is lost. The ground responds. Patterns shift and reorganize. This process can be tracked across seasons. Each cycle modifies the terrain slightly differently. Sublimation proves that even without liquid water, Mars can actively sculpt its polar landscapes through simple physical transitions, driven by sunlight and seasonal temperature change. Fractured mounds rise along the southern edge of Elysium Planitia. Each mound spans several kilometers and reaches roughly 60 meters in height. Cracks stretch across their surfaces. These fractures are extensional, pulled apart rather than crushed. The pattern indicates uplift from below. The mounds likely consist of solidified lava. They blend seamlessly with surrounding flood lavas. Where fractures cut deeply, rocky interiors are exposed. Weaker disrupted material lies above, especially to the northeast. Smooth lava plains fill the spaces between mounds, etched by sinuous pressure ridges. Dust and sand form a thin regional cover. Nergal Vallis merges with Uzboy Vallis near the rim of Luki crater. The surface is cluttered with dunes, boulders, and scattered sediments. As elevation drops away from the crater wall, the terrain smooths out. Gullies carve both sides of the rim. Nergal, the smaller channel, empties into the broader Uzboy. Dust hides many original fluvial forms, yet resistant outcrops persist along the southern rim. Bright patches peek through, draped in dark wind ripples. Even these hard layers show scalloped textures from erosion. Layering appears in outcrops and gully walls, hinting at water moving through this junction long ago. Candor Chasma plunges deep into the crust. Its floor lies about 4 kilometers below the rim. Thick sedimentary layers blanket the basin. Sand and dust accumulated here, carried by wind or water. The canyon may once have been filled to the top, then emptied by erosion. Elongated hills remain where rock resisted removal. Differences in grain size or chemical alteration strengthen them. The most striking feature is the swirling geometry of the layers. Originally, horizontal beds folded under the weight of overlying sediment. These deposits may record shallow lakes. Water rock reactions here could have released energy, supporting brief, habitable environments. The surface displays spider-like formations etched into the ground. These patterns test ideas about where such features can develop. Their distribution matters. Seasonal ice likely covered this area. Gas built pressure beneath the ice, then escaped explosively. Each spider traces a branching path of release. The terrain records interactions between ice, gas, and regolith, showing that active processes continue to operate where conditions briefly allow volatile trapping and sudden discharge. A circular mesa rises from the floor of West Candor Chasma. Its symmetry draws attention. The form raises a clear question. Did erosion isolate a former spring deposit, or does this structure mark an ancient impact? The steep margins resist surrounding loss. The interior remains intact. Subtle clues in shape and relief hold the answer. Resolving its origin helps separate slow, fluid-driven construction from violent impact collapse within the canyon system. Dark fans spread across bright seasonal carbon dioxide ice. Their contrast is sharp. Particles appear to descend through the ice surface. This site tests whether dark material cleans the ice as it sinks. Seasonal gas release likely mobilizes grains, lifting and redistributing them. As material falls back, fans form. These features mark active exchange between ice, gas, and sediment, driven by seasonal sunlight rather than long-term climate change. A crater floor displays concentric fill structures. Lines of pits arc across the surface. Shallow hollows interrupt the pattern. Light-toned cones rise from the floor. These cones may represent mud volcanoes. Material could have ascended from depth, releasing trapped fluids or gases. The concentric textures suggest slow inward deformation of sediment rather than a static deposit. This crater records post-impact activity that continued long after the initial formation event. A landslide spreads across the northern wall of an impact crater. The displaced mass appears broad and relatively flat. Grooves cut across its surface. These grooves trace internal motion as the slide moved downslope. Material failed as a single body, then settled. The feature captures a moment when gravity overcame structural strength, redistributing rock across the crater interior in a rapid and decisive collapse. Colofossi extend for hundreds of kilometers across Arabia Terra. At the end of one trough, the terrain becomes ribbed. Ridges rise and fall near an impact crater. This pattern reflects stress within the crust. Trough formation fractured the surface. Compression and extension shaped the ribs. Studying these textures reveals how large-scale tectonic forces deform ground far beyond the point where fractures first opened. Uzboy Vallis exposes layered deposits along its floor. Drainage was once blocked by the rim of Holden Crater. Water pooled, forming a short-lived lake. As levels rose, the lake overtopped the rim. Drainage resumed with force. Flow eroded the valley floor and exposed stacked layers. These deposits extend for long distances. Their coarse texture suggests rapid emplacement rather than slow settling. The valley preserves evidence of a brief but powerful hydrologic episode on Mars. A circular depression lies in the southern polar region. It spans 4 kilometers and sinks about 40 meters deep. Its shape resembles an impact crater, yet it may not be one. Gradual caving and collapse could explain its form. Subsurface material may have failed over time. This feature challenges simple interpretation and highlights how slow structural processes can mimic the geometry of impact events. Elysium Planitia has been repeatedly flooded by lava. An older impact crater here was filled by one of the youngest flows. Only fragments of the rim remain exposed. The lava surface broke into ridged plates. Plates rafted apart as molten material moved beneath. Compression crumpled the crust. Extension pulled it open. Later, lava inside the crater sank after a thick crust formed. Molten material likely drained through a buried gap in the rim. Near the center, small cones mark steam explosions, where groundwater flashed to vapor beneath the hot flow. Near Juvente Chasma, former channels now stand as ridges. Streams became inverted. Light-toned layered deposits spread across the plains. A dark mantle hides much of them. Where exposed, layers vary in brightness and erosion. These variations differ from deposits inside Juvente. The inverted streams also contain light layers. Surrounding weaker material eroded away, leaving cemented channel fill behind. Late fluid circulation likely hardened these sediments. Expansion of Juvente destroyed parts of the system, truncating what once extended farther east. Idaeus Fossi contains a channel carved into fractured terrain. Its shape suggests water or glacial involvement. Flow or ice movement likely shaped the surface. The feature preserves clues about cold climate hydrology rather than warm, persistent rivers. Studying it helps constrain how fluids behaved under low temperatures and limited atmospheric pressure on ancient Mars. Near Elysium Mons, a resistant mound rises above surrounding plains. It erodes more slowly than nearby terrain. Its composition differs from the regional surface. The structure does not resemble an impact crater. It may represent volcanic construction or intrusive material. Its survival points to stronger internal makeup, allowing it to withstand processes that stripped away softer surrounding deposits. In Meridiani Planum, crater ejecta spreads across the surface. Within this blanket, talc may be present. If confirmed, it likely formed through hydrothermal activity. Heat from the impact kept fluids circulating as the ejecta cooled over thousands of years. Such minerals record prolonged interaction between heat, water, and rock after the initial impact chaos settled. A pedestal crater rises above the surrounding terrain. Impact ejecta formed a resistant blanket. That layer slowed erosion beneath it. Nearby ground wore away faster. Only part of the ejecta edge remains visible here. The margin erodes into ragged mesas and buttes. A strong upper layer forms steep, sometimes overhanging cliffs. Blocks break free and fall downslope. This armor protects weaker material below. Such sites preserve rock units erased elsewhere by relentless erosion. Columbus Crater spans 100 kilometers across. Along its northeast inner wall, sedimentary layers are exposed in cross-section. These rocks settled by water or wind. Later erosion revealed their sequence. Near-infrared observations show hydrated minerals within the layers. A north-facing slope about 250 meters wide displays fine layering. Dark blue layers may be intrinsically darker or better at trapping sand than brighter ones. The exposure records repeated deposition under changing environmental conditions. Deuteronolus mensae displays ridges and troughs arranged in circular patterns. These shapes may reflect buried impact craters. Stresses from hidden structures deform the surface above. By comparing predicted strain with observed geometry, subsurface features can be inferred. The terrain preserves subtle echoes of impacts concealed beneath later deposits and modification. In Arabia Terra, a heavily modified crater lies at the boundary between highlands and lowlands. A proposed ancient shoreline cuts across it. Younger, fluvial deposits may overlie the area. Gullies slice the south rim. Sediments fill the crater floor, likely laid down by water. Two distinct floor units appear, separated by fractured terrain. Mesa walls show dense, internal layering. Landslide deposits overlie wind ripples, suggesting recent or ongoing degradation. This crater records multiple episodes of deposition, erosion, and collapse across Martian history. Thank you for being with us. Please subscribe, share, and like.